Hello, good morning.
Good morning, sir.
Yeah.
Good morning, sir.
Good morning, sir.
I hope this is where everybody is in this. I hope it is the normal class because I had problems logging into the Teams, and then eventually when I could log in, I could see the meeting already started. So I hope nobody is outside this group for today's class.
Yeah, this is the only meeting.
Okay. Now I shall continue with the last part. It was almost finished on Friday, but I will just try to show you. Just let me. Now, by any chance, did you go through the presentation? Hello? Hello? Did you have a chance to go through the presentation? Hello, students. Can you hear me? Hello?
Yes, sir. Yes, sir.
Yeah. I just wanted to know whether you could follow everything.
Yes, sir.
Yes, sir.
Okay. So I will continue. Maybe just go back a little bit and rewind and then finish this off. So I'm going to the presentation mode.
And sir, could you please start that recording?
Yeah, no need of recording. I will give you a link in YouTube where you will get this lecture again. Okay, you can replay and see it yourself. That's the GAN lecture, same lecture. Could you see everything? Hello?
Yes, sir.
Yes, sir.
Could you see the slides?
Yes, sir.
Yes, sir.
Okay. So in the last class, I had been discussing about the effects of bone remodeling and how this, the changes in bone density, particularly around the prosthesis or around the inclusion of the prosthesis, the area or the neighborhood of inclusion of the prosthesis, how the bone density changes due to the effect of bone remodeling and primarily owing to the inclusion of the prosthesis. So the prosthesis is an artificial element that is used for reconstruction of the joint, and let me project this. So the prosthesis is basically an artificial element that is inserted inside the human body, and this, on the one side, the benefit is that it is used for reconstruction and to offer normal movement that was existing in case of a normal patient who has been affected by bone degenerative diseases. And this inclusion of the implant actually has different types of effect that we will discuss later on separately. The implants, the failure mechanisms, all these things. But what is one of the most important or fascinating properties of bone that has been exhibited in this sort of simulations is that the bone adapts its structure according to the mechanical stimulus it receives. Okay, so all these simulations actually presents how this phenomenon of bone remodeling is occurring after inclusion of the prosthesis. Okay, so in this slide we can see that the acetabular component has been inserted in a natural pelvic bone or the hemipelvis, and if you see the, just let me put on the pointer. If you see this submodel, this on the left side is the full scale model of the pelvic bone with the acetabular component of the acetabular prosthesis inserted in place. Okay. On the right is a submodel of the same structure. Okay. But you can see here it is truncated. Okay. So the majority portion of the pelvic bone, which is a large bone, has not been included in this structure. Right? So the truncation is about here, which means somewhat about here is the truncation. Here and here and here. Okay? So majority portion of the pelvic bone is not included in this submodel. However, the elastic property, the elastic behavior of the pelvic bone still can be included in this model by transferring the nodal displacements from the full-scale model to the submodel. Okay, so the nodal displacements are key. These are displacements. So the displacements at these nodes, if there are more nodes, because the submodel is actually a much finer model compared to the coarse full-scale model. So you may actually have a little bit more number of boundaries. So when there is more number of nodes, you have to extrapolate or interpolate the displacements at these nodes. Basically what you do, you transfer the nodal displacements at these cut boundaries from the full-scale model to this submodel. Now how do you assess the whole procedure? Okay, as I told you in the last class, that this is similar to modeling aerospace structure. Okay, so first you have a coarse model of the full aircraft, for example. Then if you are interested in certain portions of the aircraft, say the wings, the tail, or whatever, there may be several parts, you can make a very fine model because you are interested in more precise values as compared to the coarser model, which can give you more, less accurate values. So the finer the model, generally, the better are the results. Because at the end of the day, you have to appreciate the fact that finite element modeling and analysis is an approximate it gives you approximate results. It is not an analytical model, but a numerical technique, and therefore it is, there are many intricacies in the modeling sort of procedures and minimizing the errors, minimizing sort of different, basically discretization, minimizing discretization error, so that you can come up with more improved results. So a finer model, finely meshed model, is generally recommended for better results. Now, how do we assess or evaluate that this submodeling technique is giving you acceptable results? For that, of course, we need to compare the results of the two models. So if I try to compare the results of the two models, you can see here very clearly. So this is where the submodel has been created. So this is independent solution, and of course it has the nodal displacement at the cut boundaries. Okay, but this model doesn't have any cut boundaries. It's a full model with all the forces, muscle forces, joint reaction forces, as well as the constraints, the physiological constraints at the pubis and the sacroiliac joint. Okay. But when we compare, you can see it is mostly similar. Okay, and that's where the success of this technique lies. You see everywhere it is similar. Okay. Now, if you look a little bit more carefully, you should pay attention here, where there is a high stress gradient. Okay. Compare this portion, as I'm pointing with my laser pointer, and this portion. Similar location. This has a higher stress gradient. This is a lesser stress gradient. It's more red all through, rather than little bit interruption of orange and yellow in between. So why that is happening? The answer is that this model is a finer model, and therefore if you have a finer model, you can incorporate the description of the variation in bone mechanical properties more accurately compared to the coarse fine model, coarse full-scale model. Okay, so whenever you have better description of the material properties in critical regions, particularly where there are stress gradients, obviously it will show up in the results. So this in here, around where there is the critical portion, there is a high stress gradients, we can see there are certain deviations between, or differences between the submodel and the full-scale model. Okay, subtle differences. These are subtle differences, but grossly it is giving you the same result, which actually presents the success of this submodeling technique. Now, when we talk about changes of bone density distribution, basically the bone remodeling, you can see very clearly on the left the starting configuration, that is post-operative scenario, or you can say this is the scenario of the intact bone, because we have just put in the prosthesis. Whatever bone was there in the intact position, which has been retained, are still there. Okay, the properties have not changed. The property starts to change immediately after the surgery, given the full loading condition. Okay, so the initial period, the rehabilitation period, the patient is not getting any mechanical stimulus, lying on bed, maybe supported by crutches, so partial load bearing. Once it is given the full load bearing, you can see how this bone density around the prosthesis, we call it mostly periprosthetic. Okay, the name periprosthetic means periphery of the prosthesis. Okay, so immediately around the periphery of the prosthesis, there are visible changes in bone density. It depends, of course, on the mechanics of the interface condition, the interfacial condition. Okay, here in the slide, you basically see two interfacial conditions. One is fully bonded implant bone interface. The other is partially bonded implant bone interface. Okay, these will be dealt with separately in the next chapter that I will be discussing, biomechanical modeling, where I will discuss all these mechanics. But for the time being, the interface condition also plays a role in the bone remodeling patterns around the prosthesis. Okay, and this is clearly exhibited. But as I told you, the main focus is to show you that bone remodels its structure. And remember, these papers are already published. So 2013 publication of one of my PhD student. And results have been compared with the clinical feedback studies that are performed on patients. And it has exactly, the numerical simulation exactly replicate the clinical results. Okay, so we have bone resorption near about the central part of the acetabulum, whereas you can see bone apposition both here. Why do I use these slides? Because we have both. We have bone apposition, increase in bone density, as well as bone resorption in and around the prosthesis. So around the periphery of the prosthesis, this side, you can see, compared to the first starting configuration. If you compare, you have to always compare with the starting configuration. You can see more red and orange here, more red rather, compared to pure orange around the periphery of the prosthesis. And you see the blue has increased to a great extent inside, more central part as we move towards the central part of the prosthesis. So bone apposition is occurring around the periphery of the prosthesis, whereas bone resorption is occurring around the central part of the prosthesis. So if you compare element by element, and if you try to plot in regions, say 1, 2, 3, 4, if we divide this hemisphere into 4 quadrants, 1, 2, 3, 4, and try to plot what is the bone density changes, evolutionary. So time-dependent bone density changes. Then all this time is basically this simulation time step, tau into delta t. Okay, so that simulation time state that we had calculated, assuming maximum change of 0.865, that is half of 1.73. Assuming 1.73 is the density of the cortical bone. Okay, so we have the change of bone density averaged over one region. So 1, 2, 3, 4. So there are 4 regions. We plot it, it comes out like this. You designs. Okay, so as I told you, we have prosthesis 1, which is the total thickness of the prosthesis is 4.5, which contains actually 3 millimeter thick ultra high molecular weight polyethylene bearing surface, and with a backing of 1.5 millimeter backing of CFR PBT. So together they make up 4.5 thickness, and this design is popularly known as the Cambridge Cup because it evolved from Cambridge, University of Cambridge. Okay, there has been some modification with reducing the thickness of the acetabular component, and this has been basically done with some purpose because the acetabulum actually deforms to a great extent during physiological loading. So they wanted to make it less stiffer, and therefore the thickness of the CFR, the component, which is made up of PEEK, polyether ketone. So CFR, these are all composite cups. CFR PBT and CFR PEEK are composite materials. Okay, and it is popularly known as Mitch PCR cup. So here the thickness of the acetabular component is 3 millimeter. Okay. Now both these design contains a horseshoe cut in congruence with the natural acetabulum, which has a cut like that. Okay. So it is following basically the geometry of the acetabulum, natural acetabulum. But when it all started with the very famous gold standard prosthesis called the Charnley's hip, it started with a pure hemispherical cup. Okay, it was a polyethylene cup with a stainless steel femoral component. Now, there it was pure hemispherical cup, no cutout, no horseshoe cutout. So we try to assess what happens if there is a condition when we are using a 3 millimeter, same as Mitch cup, 3 millimeter PEEK material without a cutout. Okay. So if you consider these 3 designs, we clearly see the differences in the bone density changes, the bone remodeling patterns. Okay. Prosthesis 1 is the most stiff prosthesis. So higher the stiffness, higher the rigidity, the more is the effects of adverse effects. Adverse, I stress on the fact, the negative effects of bone remodeling, the adverse effects of bone remodeling. So why that happens? Because this prosthesis, the stiffness of this prosthesis, because it is more thick, the stiffness of this prosthesis, the rigidity of this prosthesis is much more compared to the other 2. Okay, so the more the stiffness, the modulus and the thickness, more predominant will be the effect, or more pronounced will be the effect of stress shielding. Okay, you now know what is stress shielding, because stress shielding is the phenomenon by which the implant carries the bulk of the weight, which was earlier carried by the surrounding bone itself, thereby resulting in a situation where the bone receives much lesser mechanical stimulus as compared to the natural situation. Okay, so obviously the effects of bone resorption would be much more, but still you can see the red areas being generated around the periphery, the prosthesis. So that means bone apposition also can be observed in the case of a thicker prosthesis. But as you move to a midge cup, you can see the effect of bone, adverse effect of bone remodeling is much less. Okay, whereas you can see some bone apposition also inside the acetabulum, which is, this is the immediate poster. You should always compare with this situation. You can see quite favorable bone apposition inside the acetabular cavity, which was earlier not the case. So, but there is some adverse effect still of bone remodeling, indicated by the dark blue and light blue here. Now for the same prosthesis without a cutout, you can see here the effect of adverse bone remodeling is much more as you compare prosthesis 3 with prosthesis 2. Now, if you look into the cross-sections through the acetabular cavity, so this is the natural bone, as you can see, but of course operated. So it is the starting configuration after insertion of the acetabular component. Okay, section 1, 2, and 3. Comparatively, the 3 millimeter thick implant, you can see the adverse bone remodeling effects is quite prevalent already with the 3 millimeter thick implant. Now this thickness can also go to 11 millimeter. So as you increase the thickness, the adverse effects of bone remodeling becomes more and more pronounced. Okay? This is mainly because a thicker implant will give rise to a stiffer implant and a more rigid implant, and thereby the effects of stress shielding will be much more as compared to a thinner implant. Okay, so we see here very clearly through the sections the adverse effects of bone remodeling. So we can summarize the findings as the effects of stress shielding, stress, strain, whatever shielding, was observed in the central part of the acetabulum, whereas a pronounced increase in strain was observed around the periphery of the acetabulum. Okay. Now this is out of stress analysis. Stress strain shielding was considered higher for the bonded, so this is not important for you at this stage. Okay. Now horseshoe-shaped CFR peak appears to be a better suited alternative bearing surface than other designs with regard to stress strain shielding, bone deformation, and bone remodeling. Okay, so we can only concentrate on stress strain shielding and bone remodeling at this moment. As I told you, bone deformation, it is important to mimic the deformation of the acetabulum in the natural situation, but we can talk about it later. Not at this moment. Let us focus on bone remodeling itself. The thickness of the acetabular component also played a crucial role in the implant-induced bone adaptation. Okay, this has been very clearly exhibited in the results in form of figures. Now, another interesting result that to summarize the effect is in the case of a hip replacement of the femoral side. Okay, so we are talking about taking the example of hip, but the hip has a femoral implant and acetabular component. Okay, so this is a typical uncemented, or we'll talk about cemented, uncemented in the next lecture. But to start with, we have an implant quite an implant. So it's something that goes inside, and we are taking the sectional plot, and you can see the bone density distribution at the starting point, the post-operative situation. So in long term, say when it has reached equilibrium of the structure, we can see in the proximal part of the femur, the negative signs means that in this area or volume of bone, the bone density is reduced 67% as compared to the original situation, this situation, okay? The starting configuration. Minus 55% in the bone volume on the other sides. So this is the medial side, this is the lack of the proximal end implanted structure. As you move down, is minus 42% on the lateral side, minus 36% on the medial side. These minus signs means it is bone resorption phenomenon. It's bone resorption. Whereas a plus sign, as you will go down, I have not plotted it, but almost near to the distal end of the implant, you would see some bone apposition. Okay? But the interesting result is this, which is well supported by clinical feedback studies, and nowadays you have DEXA scan, okay, dual energy absorptiometry scans, and those give you bone density in a region, small region. So we can directly measure bone density in a living person in vivo using these DEXA scans. Okay, so it is now much easier to track the changes in bone density in vivo. Now on the other side of the figure, the right hand side of the figure, we see another prosthesis, another design of the femoral implant, which is thinner and slimmer as compared to these bulky prosthesis. Okay, and this has come out as a result of optimization. Okay, three-dimensional design optimization. So here you see that the reduction in bone density is much less. Okay, so bone remodeling effect have reduced drastically from 67% to 28%, from 55% to 18%, from 42% to 4%, and from 36% to 10% in this region. So if you can appropriately change the design of the implant, the tissue response, basically bone remodeling is a tissue response due to insertion of the implant. Okay, so the tissue response will also change drastically. So can we have some questions or query to be answered? Hello?
Sir?
Can you hear me? Yeah.
Sir, if we remove the implant at some later stage, like one day you were discussing, like, so what happens?
No. We cannot remove implants because you can see already that when we insert an implant, there is, it is basically something we try to do it a permanent. It's a permanent surgery sort of thing, a permanent inclusion, because that will, it is a reconstructive surgery. Okay, it reconstructs the joint and it offers you the the range of movements that was existing in a natural case. Okay, when does a patient go for a joint replacement? So when the patient is severely affected by bone degenerative diseases, he may not be able to walk, or even he is walking with a huge amount of pain. Okay, so then seeing his clinical condition, particularly the condition inside the joint, as we have discussed about bone degenerative diseases earlier, I will again discuss it with more stress. A doctor recommends a joint replacement surgery. Okay, and there, as you can see here also in the picture, that the distal part of the femur, the proximal part, the head to neck, has been resected. Okay, it is cut off, and then the implant is pushed in. Okay, it may be a cemented fixation, it may be an uncemented variety. So they stay there. If it is a total joint replacement, total hip replacement, you have a femoral component with a head. The head is not shown in this bone remodeling simulations, but the head is there, and that head basically articulates with the acetabular component. Ideally, if it is a total joint replacement. Okay. Now, if the surgery is not well done, the patient may be still complaining about some pain. There are some rectifications done in form of a revision surgery, right? In form of revision surgeries, but never the implant is taken off. Okay? The implant is there to reconstruct the joint and offer you the normal range of motion. Okay. Next question, please.
So this idea of strain shielding, which is increasing when we made stiffer designs, I mean the design of processes which are thicker, is a little bit counterintuitive to me, because if we make more stiffer designs, then I think like strain should increase, and maybe bone resorption density bone resorption should decrease. Can you please elaborate on that?
Yeah, I will talk about that, okay, separately, because we will move now inside the implants and all these things. More in-depth knowledge about implants will be shared with you. Implant design, the effects, the good effects, the bad effects. Now, to be honest with you, I have worked in this field for more than 25 years. And what has evolved is that this implant design is a compromise solution to various requirements. Okay. And these requirements are quite contradictory in nature. Okay. Say, for instance, as you has remarked, that if you make the implant more stiffer, what is wrong with it? The first thing is that if you make it stiffer, you can get, the adverse effects of bone remodeling to a great extent, which is a negative thing. If bone remodels, in the periphery of the prosthesis, the whole structure, imagine a house being built on a soil which is highly susceptible to erosion. Okay, what will that happen? What will happen eventually? The structure will subside. There will be subsidence. You have seen probably that some houses near big rivers have been swept away, isn't it?
Yes, sir.
So what happens that the bone is disappearing. in the form of reduction in density. The bone is disappearing around the prosthesis, and that is very critical and leads to failure of the structure. Okay, bone needs to be preserved for the reconstructive surgery to succeed. This is a primary requirement. So obviously, any change in design, I mean in dimensions, dimensional change or basic design changes, is associated with changes in the stiffness of the implant, which has direct effect on bone remodeling. Apart from that, we have also effects in interface stresses. Okay, the stresses that is occurring at the interface. So high interface stress mismatch of stiffness between bone and implant will always lead to high interface stresses, and that high interface stresses will lead to implant being debonded from the host bone. Okay, so there is separation of the implant and the bone, or implant and the cement with which it is fixed. Okay, so I'll show you more figures in the next day, because we have not discussed the implant, mechanics too elaborately. Before that, I have discussed about bone. Okay, and just to show you, just get a feeling of what bone remodeling is, I have shown you certain slides, but immediately after this lecture, the next lecture which will be following will show you the basics of the implants, implant design, and the problems associated with the implant design. And these, requirements, we are trying, design has to be, in a way, a compromise solution between different requirements. See, you cannot eradicate bone remodeling. Let me tell you one thing. Okay? You can reduce the effect. It is like flood control. Okay, can you eradicate earthquakes? Can you eradicate floods? No, these are natural phenomena. Okay, this is also a natural phenomenon, but you can control it through designing an optimum implant, so that the failures, the chances of failure is reduced. Okay, do you get my point?
Yes, sir.
Anything else? Yeah, good questions. I appreciate, at this level, even if sounds silly to me, I am more than happy to answer questions, because I understand this is a new subject and a completely, for you, it is not so easy to understand. And that's the reason I'm going very slowly at this point of time. Anything else? Okay, I think it is 10:50 now, 50. So if you do not have question, I will start the new topic and in the biomechanical modeling as well as a bit of implants in the next class. But we don't have too much time anyway to start a new topic. But before that, let me, have you all got the marks of the major test 1, which is a sort of equivalent to the midsem? Hello. Okay. So there were certain discrepancies. I think that has been sorted out. Particularly in the MCQ.
Yes, sir.
Everybody is happy with with the final marks. I think SEBI is directly taking care of that, right? Hello. Hello. Hello.
Yes, sir.
Okay. Now, how far are you with today's 10th of March? So within 5 days, you are supposed to submit the assignment. What was that assignment? Assignment number 3, right?
Yes, sir. That's right.
Yeah. Assignment 3. So if there are 4 to 5 students in a group, so one member should upload. Okay, and don't try to make it more than 2 to 3 MB. Okay, PDF files 2 to 3 MB. One person would submit in his account, and when we actually open the first page, there the names and roll numbers of the other people should be clearly written so that we can tally with the students, okay, who have submitted and who have not submitted, right? There should not be any ambiguity. Okay, if it is 4 students, put the name of the 4 students. One student take the responsibility of submitting it in his account, in his or her account, and the rest, because there is the names of the other students, we will tick that these students are together, so they have all submitted. Is it clear? Hello?
Sir, so remaining
Yes,
students have to turn in, or
remaining student need the other students need not submit, because we will be actually, but what to do in the teams, it will show up, right? So let me discuss that with SEBI. Okay, from the point of view of the teams, what happens? The other alternative is everybody submits. It's this, the report. If you are in a group, all the group members submit basically in his account, respective accounts. That's the other alternative.
So you can assign group numbers to each group, and then for one group number there is one submission.
Yeah, but that has to be done. We are not. We don't have that information which student belongs to which group. Let me discuss with SEBI. Okay, what is most convenient method of submission, right? Okay.
Okay, sir.
Any other query? I would what I would do is give you the link, the YouTube, like in the YouTube you will find the same GAN lecture, okay, of mine on the mechanical behavior of bone. So so what happens is, in the GAN when you give the GAN course, Sanjay Gupta, Orthopedic Biomechanics, Implants and Biomaterials, they will give you several day-to-day lectures. Now, for this lecture, it is day 4, but in day 4, I am presenting. Before me, Nico Verdenscott is also presenting. So, in that full day, there are several lectures. Okay, so It may not be the first lecture, it may be the second lecture. So I will indicate that clearly, that this is the link for the full day lecture, but my lecture on this topic is the second lecture or the third lecture, as the case may be. Right? Is that clear? Is it clear? Abhinav?
Yes, sir.
Yeah.
Yes.
Yeah. The problem is I have to always ask you because I don't know what is happening in this online mode. Sometimes you may receive my voice or you may not receive. That's the reason I have to check every time when I'm giving you certain important instructions. Anyway, have a good day and see you tomorrow.
Sir?
Yeah.
Sir, could we get an extension for the term project submission since all of the 4-year students have their grand viva this week and some of us have our viva next week too, early next week?
I know that. I am taking grand viva today. 4th-year students, right?
Yes, sir, 4th-year students.
So I am in the board of Professor Shubhranshu Roy. 5 o'clock it starts. So how grand viva? How long do you want this extension of this project?
So maybe another 3 or 4 days.
Let us extend it by 1 week.
Yes, sir, that would be great.
But no further extension.
Yes, sir. Yes, sir. I've already asked you for a lot.
Okay. No further.
Yes, sir. Thank you so much, sir.
So 22. So I will change the date. Okay. But 22 should be enough. If you cannot submit, you are not willing to submit. This is what I would conclude.
Thank you, sir, for accepting the request.
Thank you.